Okay, this is the second hour of Physics 1C for March 9th, and we're going to keep talking about electric potential. We just talked about a definition of electric potential when you have a uniform field. Zoom out a little bit here. Uniform field. And we said that it looks a lot like the potential energy due to gravity. And so we want to kind of generalize this idea. So to do that, we got to go back to the way we define the work right here. So the work that's defined by this definition is the work done by only a uniform or a constant force. The work done by a constant force. If the force is changing in some way, we get a little bit different definition, and that'll provide us with kind of the more general definition of what electric potential is. So to do work done by a non-constant force, a force that changes, or a force where the path changes, you need to do this. Okay. And the work done by the force then is the integral now of the force dot product with ds. This is something that's called the line integral. And if you've taken 220, you've probably learned a little bit about this. Anyway, that's the definition of the work. And then keeping in mind that the work done is equal to the negative of the change of potential energy, which is the same thing that we used right here. Then we can equate this to the change of potential energy. So we can say that delta U negative should be equal to the integral of f dot ds. But now what we'll do is, just as we did before, we'll replace the force, because the force is always going to be q times the electric fields dot ds. And now we'll do the same thing as before. We'll divide the q to the left-hand side. I'm going to move the negative sign to the right-hand side. So delta U, we divide the q over here. Charge is always going to be something that's a constant. And so we end up getting the negative integral of E dot ds. And we'll see how to apply this soon. We're just working on a definition, right? So the idea is that we start from the definition of work. We replace everything that we can, such as we replace force with Q times E. And we're going to get the delta U over Q so that we can use this definition right here. We know that if we take the change of potential energy and we divide by the charge, that's going to give us the change of potential. So then this is our most general definition of what the electric potential difference is. So I kept calling it electric potential, but usually the way it's described is we call this electric potential difference. So it's electric potential, which would just be V. I called it change in electric potential up here. So it's often called just electric potential difference. And different textbooks write this in different ways. But what we can do with this is we can say, well, if I really want to have the right-hand side and the left-hand side make any sense here, I need to have limits right here, right? So normally it's written something like this. You take the integral between 2 points, point A and point B, using whatever, it could be x1 and x2 or y1 and y2 or whatever, but it needs to be just between 2 points of E dot ds, and that should be equal to the potential at point B minus the potential at point A. Sometimes it might be defined as the potential of point B relative to point A. But that is our kind of most general definition. Now your textbook, how does your textbook do this? I think what your textbook does, and I don't really like this, but your textbook does it like this. They write VAB. They don't use the delta sign. That's the part I don't like. They use VAB, and they say that this is equal to the. They don't even put a negative sign on here. They just write it as, how do they do it? They do the integral, and they swap the limits, so they can hide the negative sign for some reason. I don't really understand it. So I believe this is the way that your textbook writes it. Other textbooks that I've used always put this negative sign in here. So, I don't know. I vastly prefer the definition that I have boxed here. because it is very clear what's being stated, right? The potential at point B minus the potential at point A is equal to the integral from point A to point B of E dot ds. And this should be pretty consistent with the way that you do integrals, right? When you do an integral, you do the top minus the bottom, right? You know what I mean? So that's the definition that I like to use. And we'll look at some applications of this. Delvino says, you wonder how humanity would change as a whole once we've been exposed to so many varying environments. That's a great question. It's a great question. Living in space definitely affects people. So there was like, there's these two twins that are both astronauts, right? What is his name? He's bald. I can't remember what his name is. I think he's a senator now. He's from Arizona. Does anyone know who I'm talking about? It's like
a bald twin.
Something Kelly.
Kelly, yeah, Kelly. Scott Kelly or something like that. So
I know what you're talking about.
So he has an identical twin, and he lived on the ISS for a really long time. He was on the ISS for, I want to say, a year or something like that. And then when he came back to Earth, he was like an inch taller than his twin. Because, living in space, you don't have gravity like pushing down and like squeezing your vertebrae. And so he literally got taller. So who knows what being born in space and growing up in space could do to someone's body. You might get really tall. Does anyone here watch The Expanse?
Yeah. They also say the bone density, it drops, right?
I think that's right, yeah. So you have to take bone density supplements or something like that. Do any of you watch The Expanse? Anyone know what that show is?
I do not.
Oh, that really surprised me. I figured at least somebody would have seen this show. It's on Amazon Prime. It used to be on Sci-Fi Channel. But there's literally people in that show. It's a pretty well done show because like they put a lot of like the physics and the astronomy and stuff. They do a pretty good job with it. But there's people in that show that grow up. They're called belters. They live in the asteroid belt and they basically farm the asteroid belt by mining the rocks and ship around precious metals and stuff like that. Make money that way. Because they live in space, they're like taller than normal people. They have like they physically look different than normal people. That they grew up on a planet or something like that. So they have that, and they've also got people. Anyway, so yeah, I think there's unquestionably living in space, living on different planets would change humanity for sure. We would become different, just like the Galapagos Islands, right? Where Darwin figured out how evolution was working, where he saw certain types of birds and stuff that were living on one isolated island would adapt to their environment, and then over time, yeah. Won't your legs be underdeveloped though? Yeah, so I think the idea would be that gravity would actually hurt you, Raccoon. If you were to go to a normal planet, you wouldn't be used to gravity unless you'd been living on a space station that had artificial gravity by rotating or something like that, right? Yeah, I think your muscles would be underdeveloped. Of course, if you knew that was a problem, you could just do exercises, right? Like on the ISS, the International Space Station, they do resistance exercises, like where you have the ability, you can actually keep your muscles from atrophying and stuff by doing those type of exercises.
Do you know if some things grow like in a different form up in space?
I don't know. I know we grow things in space, but I know they do. Those are some of the experiments they're doing. Is like what kind of things can grow in space and how does it alter things. But I don't know much about it. It's an interesting idea though. Okay, so let's look at some applications of this idea, this new idea of electric potential difference. And again, if this equation looks hard to you, trust me that when we actually use the equation, it's not going to be that complicated. Okay, so I'm going to highlight some equations here that are important. So we're going to need this one. Delta U over Q is equal to delta V, but I'm going to write it in a different way. I'm going to move the Q to the right-hand side. I'm going to write delta U, the change in electric potential energy, is going to be equal to Q times delta V. You're going to want to remember this equation. This is going to be really useful to you in your homework. Change in potential energy is Q times delta V. Okay? And then we'll just use this equation in this problem so we can see how it works. Put this over some. This one over some. All right, so here's our problem. The motion of a proton in an electric field And it says a proton is released from rest at point A, right here, in a uniform electric field that has a magnitude of 8 times 10 to the 4 volts per meter. This is the other version of unit for electric field now, right? So our units for electric field are kind of bigger now. So our units for E, what we have now is newtons per coulomb or volts per meter. Numerically, these are the same. Numerically, these are exactly the same. Or not numerically, dimensionally, they're the same. You work out the units, you get exactly the same thing for both of these. You can try that out yourself. So here we have the uniform electric field has a magnitude of 8 times 10 to the 4 volts per meter. The proton undergoes a displacement of d equal to 0.5 meters to the point B in the direction of the electric field. So it moves from here to here, which is the natural direction it would move in the direction of the electric field lines. We want to find the speed of the proton after completing the displacement. Right? So our goal here is to find what is the speed down here that this proton gains by moving through this field. Okay. All right. So to do this, what do we have? We're given the electric field magnitude, right? So our idea would be, since we have the electric field, we'd like to know what delta V is. So that's the first thing we're going to try to do here, is we're going to try to calculate delta V. And we're doing that because if we know what delta V is, we can find the change in potential energy, and then we can use this equation that you probably remember from Physics 1A. The work done by non-conservative forces should be equal to the change in the kinetic energy of the particle plus the change in the potential energy of the particle. So if we know what the change in kinetic energy is, we can find velocity. That's our goal here, ultimately. So that means steps would be, first of all, find delta V, then use this equation, and then use this equation. Okay? So as written above, it says delta V is equal to the negative of the integral of E dot ds. In this case, what we'll do is we'll say for ds, what that represents is going to be a infinitesimal displacement in this direction here. And I guess what we'll do is we'll just make down positive. We'll make this the positive y direction, let's say. Which means we can define this point right here to be y equal to 0, the starting point. And then we can define this bottom point right here to be y equal to d. Like that. Because it's a distance d below, right? All right. So what we're going to end up doing here is basically re-deriving what we've already found in the first part. It doesn't hurt to do that just to get familiar with how this equation works. Okay, so delta V is going to be equal to the negative of the integral of E dot ds. Now, what do we know about the electric field within this region between points A and B? Is it going to change between points A and B?
No.
No, because we know in this problem that it's a fixed value. It's 8 times 10 to the 4 volts per meter. In addition, we also know that the angle between E and ds is equal to what?
0.
Is 0, right? So the dot product disappears. So basically, this should be familiar to you if you've been doing your Gauss's law homework, that you just pull the E out, and you just end up getting the integral of ds. And realistically now, it's like the integral of like dy, basically, because we're using things in dy, okay? So we'll just write it as the integral of dy now. And we'll be integrating from, what, 0 to d, right? I don't know if that's hard to read. It's probably hard to read. Integral from 0 to d. Okay, so that's going to be negative e times d minus 0. So now we get that delta v is equal to the negative of the electric field multiplied by the distance. Pretty simple, right? And I think that's exactly what we have up here. Oh yeah, there it is. E times delta y is equal to delta v. You're going to want to remember this one. I'm going to tell you to remember this. You'll all forget it, but I'm just going to tell you now. You want to remember this. Delta v equals ed. Negative ed. Not positive ed, but negative ed. Got to remember this one. Anytime you have a uniform field, you're going to know that if you're given a field and a distance, you can find the potential difference. If you're given a voltage and you're given a distance, you can find the electric field. Okay? In this case, we're given the field, And we're given the distance, so d is equal to 0.5. So we can use that to find delta V, basically, right? And normally I just leave that till the end of the calculation, but let's go ahead and let's put it in. So negative 8 times 10 to the 4 volts per meter, multiplied by d, which is 0.5. See, the meters cancel out and you get volts. So you get delta V between these two positions is equal to 4, right? Negative 4 times 10 to the 4 volts. Now, the fact that it's negative, if that bothers you in some way, all that it means is that the change in electric potential when you go from A to B is that the electric potential is going down. Now, the way I like to think about this when I'm trying to understand this stuff is to just replace voltage with altitude, okay? What happens to the speed of a ball when it goes from like a high point on a hill to a low point on the hill? Does it increase or decrease?
It increases.
It increases, right? You put a ball at the top of a hill. It starts off at some position. It rolls down to a new position. And its speed goes up, right? Comes off with some velocity. It can start up here with v equal to 0. And this is little v, velocity. And it rolls down to here, right? So it gains energy. What happens to the change of potential energy, though?
Increases.
Negative.
Yeah, it could be something like negative mg times basically just the height right here, right? Height. So see how then you get a change in potential energy that's negative. It's the same idea over here. You've got a change in voltage or an electric potential difference that's negative. So what's this electric potential difference going to do before we even look at the rest of the problem? Well, it says you're going basically downhill. That's what the negative sign says. It says you're going downhill. So you're gaining kinetic energy. Does that make sense? So a positive charge, when accelerated through a negative potential difference, will gain energy. Just like a ball gains energy when it rolls down a hill. Okay? All right. So that's delta V. You have to leave the negative sign here, as you will see when we do the equation here. Or at least I hope so. So now we have to think about how to use this information. So we have delta V, and we want to apply our work energy equation or our conservation of energy equation, whatever you want to call this. So we first have to ask, what is the work done by non-conservative forces in this case? Are there any non-conservative forces acting? So the electric force, that's a conservative force. That doesn't count. Any non-conservative forces? Is there any friction, tension, buoyancy? No. Nothing like that, right? Okay, so this part's going to be 0, as will commonly be the case in this class. So what we have is 0 is equal to, change in kinetic energy can be written as 1/2 mass multiplied by, it looks like the problem is using VB and VA. I don't know if you can see that, so we'll use the same kind of, it's going to be, the change in kinetic energy of this particle is going to be 1/2 mvb squared minus VA squared. And then here's the thing you need to remember when you're doing these problems. Basically, whenever you see delta U, okay, you just write this. You just write Q delta V. You just replace it. Because you should be able to figure out delta V. It's either going to be given in your problem, or you're going to be given information by which you can calculate it. Okay? You know, in a given problem, they might just tell you, they might just give you this value. They might say delta V is equal to this or whatever. So there we go. And we can simplify this equation a little bit because we know VA in this problem is 0. The particle is released from rest at this location. So that's 0. So really, we just need to solve for VB. So we'll put all the numbers in at the end. Let's rearrange. So we're going to get negative Q delta V. We move that to the left-hand side. Is equal to 1/2 the mass of our particle times the velocity b squared. We want to solve for VB. So we'll get negative 2Q delta V divided by the mass. We take the square root right here. And that should give us a value for VB, which we can calculate. We will also, of course, need to have the mass of the proton, which I'll write right here. The mass of the proton is about 1.67 times 10 to the negative 27 kilograms. So if we plug that into here, what we're going to get is -2. So Q is the electron charge, or the proton charge. They have the same charge, 1.6 times 10 to the -19 coulomb. We multiply by delta V. Now, before we even put this in here, you notice you have this square root of a negative right here? Is that bothering anyone? There's a square root of a negative here.
Well, our delta V is negative, so
your delta V.
okay.
Yeah, exactly. So now you can see why delta V being negative is a good sign, is a good thing, because it's going to cancel out with this negative sign here. Okay. Yeah. All right. So -2 times 1.6 times 10 to the -19, and then multiplied by a -4 times 10 to the 4 volts. All of that divided by the mass, which is super tiny. Squared it. And we get an answer for VB. Now, of course, we could have done this problem by just using kinematics, right? I mean, we could have used a kinematic equation. We could have found the acceleration of the particle. We could say we know the initial velocity. We know the distance. We can just use that equation that's like VF squared equals V naught squared plus 2A delta X. Yeah, we don't have to. You can also do it with energy. And doing it with energy means we're going to be able to use this method when the force is not constant, such as, for example, when you're near a point charge, which will be the next thing we'll do, where, you know, that's what's valuable about this, is we can not only use it to solve problems that are simple like this, but we can also use it to solve problems that are really complicated. All right. So I get, what do you all get for this one? It looks like it's going to come out.
Like 2.8 times 10 to the 6.
Yeah, I agree. So I got 2.8. We'll say 2.83 times 10 to the 6th meters per second. This is actually about 1% the speed of light. Almost exactly. Because the speed of light is 3 times 10 to the 8, and this is about 3 times 10 to the 6th. It's pretty fast, right? 1% the speed of light. And it's not that hard to produce. You just need to have a voltage between the two plates of, well, some size like that. So you need a really big battery to produce this. In fact, this is exactly how we accelerate charged particles. Is you basically pass them between charged plates like this. Right? And usually what we do is we just say, okay, you've got your positive plate on this side. You leave like a gap. So you got a positive plate here. And on the other side, we got a negative plate. Again, you leave a gap. And then what you do, so there's a potential difference between the plates now, because there's a field. And, you know, maybe it has some value like this, like 40,000 volts or whatever. And now what you do is you pass a particle through there, so you've got a little proton, and you just inject it into this region here. And what happens is it gets a little boost. So when it comes out on the other side, it's moving faster. Maybe way faster. That's kind of what this problem's about. But this is literally what we do to accelerate particles. You just pass them through these voltage gaps. And every time you pass through, you pick up some speed. And you just repeat the process over and over and over again until the particle is going fast enough. And we'll talk about how you could do that. But basically, you can actually force this particle to go in a circle, so it keeps going through the same path over and over and over again, and it'll basically get a kick of energy every single time. Is that how railguns work? So my idea of what a railgun is works off of magnetism. But this could be used to make an ion gun. This could be used to make like an ion gun, I think, where you could fire ions. A railgun is like something that we will definitely talk about in this class, though. We will talk about railguns later on. Now, I don't want to be too, like, fuddy-duddy about it. Like, maybe I'm wrong, and I don't know that there could be a type of railgun that works like this, though, Delvino. I don't know. Anyway, so that's our final answer for this problem. Does anyone have any questions? Yeah, there's ion cannons in Star Wars. That's right. There's also ion propulsion that works off of this concept. If you guys know about that, there's a type of ion propulsion you can use in space to move around by shooting ions out the back. It's a pretty high efficiency but low impulse type of drive that you can use to navigate through the solar system. Alrighty. So I want to talk about this equation real quick here, because it allows us to develop a another type of energy, another unit for energy that happens to be really useful. So if we look at that equation, which I'll just rewrite down here, we're going to talk about what are called electron volts. So if we look at that equation, it says that the change of potential energy for a particle that passes through a potential gap of delta V is equal to Q times delta V. So what we can do is we can set up a type of energy where we make the charge of an electron, and we multiply that by the unit of this, which is a volt, and we get an electron volts. And what we can do is we can actually figure out how much energy an electron volt is. This is a measure of energy. And in terms of joules, what we can do is we can say that the size of the electron charge is 1.6, the same as this one up here, times 10 to the negative 19 coulombs. And you multiply that by what a volt is, which is 1 joule divided by coulomb. And that gives you a unit of energy. So I said delta U up here, but we'll just say energy. And that type of energy is 1 electron volts, and it happens to be equal to 1.6 times 10 to the negative 19 joules. Electron volts. This is a conversion factor. You could easily Google it on the internet. You can say, what is 1 electron volt in joules, and this is what it's going to give you. And it happens to be exactly the size of the electron charge that shows up here. Okay, so why do we care about this? Why would we use electron volts? Well, because it provides a standard for understanding how much energy an electron would gain if it passed through exactly 1 volt of a potential difference. So if I have a potential difference, that this is positive and this is negative, and I tell you that it has a potential difference of 1 volt, then an electron that was placed inside of here, like right here, would gain, when it goes from here to here, it would gain 1 EV. It gains that much energy, which is a tiny amount of energy, right? But for an electron, it's not a tiny amount of energy. For an electron, that amount of energy could actually give it quite a bit of speed. And so, yeah, that's what we use. It's a really kind of handy measure of energy that we can use for small particles. And in addition to that, let's look at this equation. So if we wanted to convert what we have in this part up here to electron volts, I would say that okay, is this going to work? I don't know if this will work or not. Let's see what happens. So it's -2. We have Q times delta V, but that's this times this, right? So that gives us a certain amount of joules of energy, right? If we wanted to write it in electron volts, we would just write it as the number of the voltage right here. So -4 times 10 to the 4 electron volts. Does that make sense if you look at this equation and compare it to this one up here? That you would just divide by this, and it would give you the unit in electron volts? Does that make any sense? And then what you do is you say the mass of the proton. So there's another way you can actually write mass if you use electron volts. And to understand how it works, we need to use Einstein's equation. That energy is equal to mass times the speed of light squared, which means that we can define mass by taking our unit of energy and dividing by the speed of light squared. Okay? And if we do it this way, then the mass of the proton, okay, ends up being equal to about 938 mega electron volts divided by c squared. Okay. I'm jumping way ahead in your physics studies, but I'm pretty sure you have all seen this equation before, right? The P is just for proton. That the energy of a particle is equal to mass times c squared, right?
Yeah.
Okay. So if you were to go in your textbook and look up the mass of the proton, it's going to give you two different numbers. One of the numbers it's going to give you is this one. That's in kilograms. The other number it's going to give you is this one, in MeV over c squared. So let's see why that's useful. Let's plug that into our equation right here. So 938 MeV, big M is mega, which is times 10 to the 6th, right? Is it 938? I don't know. I think that's right. I'm tempted to go look up in the book. Let's just say that it's right for now, and I may be wrong. So EV over c squared. So look at what happens. These electron volts cancel out. And you should get the same answer. Let's see if you get the same answer. I don't know. Let's see. It's going to be in terms of the speed of light, though. So it's going to be 2 times 4e4. There's a negative sign in here, too, that I left out, by the way. I'll put it back in a second. Divide by 938. So I end up getting... That has to be raised to the 0.5 power. My pen. Where'd you go? It's usually on my desk and I can't find it. Oh? Sorry, just give me a second. How could I have lost it? I just had it a second ago. Well, this is kind of weird. Maybe we should just take a break. Let's just take a break right now. And I'll try to find my stylus. What is it going to be? We'll take a break until 4 o'clock.